Hi there, and welcome back to the channel. Throughout this series of videos, you will be introduced to topics in optimal control and estimation in a way that you can draw almost complete idea about optimal control and optimal observers. Most of the introduced materials during this journey is borrowed from the book, Applied Optimal Control, Optimization, Estimation, and Control, which is written by Arthur Bryson. This is the fourth part of this series. In the last three parts, we have covered the necessary and sufficient conditions for obtaining stationary points and specified them as minimum or maximum points. In this video, we are going to address the optimum solution around the optimum point. Occasionally, we wish to find how the optimum solution changes if some of the constants in the constraint equations are changed by small amounts. Let us suppose that our following constraints are changed by infinitesimal amounts so that we have f of x and u equal to df, where df represents an infinitesimal constant vector. Thus, we can also assume that the values of x and u at the minimum solution will be changed by infinitesimal amounts dx and du. As a reminder, the conditions for a stationary point are given as where the function h is the combination between the performance index L and the constraint vectors f of x and u through the multiplier lambda. One can write the expression of the infinitesimal amounts as shown. Keep in your mind that the partial derivatives are evaluated at the original optimum point. These infinitesimal relations give 2n plus m equations for dx, du, and d lambda. Now observe the last relation. Here, for du to determine dx, the partial derivative of the function f of x and u with respect to x has to be non-singular. Thus, it follows from the first and last relations that we can write expressions for both delta lambda and delta x as shown. And if we substitute both these relations into the second relation and then solving for du, we would have the following result for du. Here, the constant c is given by the shown result, where the second partial derivatives of the function L with respect to u is given by the shown relation. This last relation is same as the sufficient condition for optimal problems with equality constraints, where its definite properties are used to specify whether the stationary point is maximum or minimum. Thus, for instance, the existence of neighboring optimum solution is guaranteed if the original point was a local minimum. That is, the second partial derivatives of the function L with respect to u is a positive definite matrix. Moreover, if we go back to the expression of dx and substitute it along with the condition where the partial derivative of the function h with respect to u is 0 in the corresponding expression for the change in the function L, which is given as shown, then we will have the following shown result, which is correct to the second order. As a reminder, the expression dl is resulted when the sufficient condition for optimal problems with equality constraints was processed. This is another proof for the condition on having neighboring optimum solution. Not to forget that we have driven the following expression for changes in u. And again, if we introduced this result into the expression of dl and did some manipulation, we would end up with following result, from which we can derive the first partial and second partial derivatives as shown. If we examine these new results, we can say the followings. In order to have neighboring optimum solution, it is necessary fulfill the following conditions. First, the Lagrange multipliers are non-trivial, non-zero at the original optimal point. And secondly, the stationary points fulfill the necessary and sufficient conditions for optimality. To sum up what we have stated, I can say the following. Given an optimization problem, minimize or maximize f of x subject to h sub I of x equal to 0, where I is starting from 1 and ends at p. The condition for the existence of neighboring optimal solutions in this context can be summarized as: if there is a point x star that satisfies the following conditions. 1. It is an optimal solution to the problem. 2. There exists another feasible point x hat different from x star that also has the same objective function value, satisfies the same equality constraints as x star. And finally, the Lagrange multipliers associated with the constraints at x star are non-zero, indicating active constraints. Under these conditions, neighboring optimal solutions exist. This implies that there are multiple feasible points that achieve the same optimal objective function value, satisfy the equality constraints, and have non-zero Lagrange multipliers, allowing for neighboring points that are also optimal. In essence, neighboring optimal solutions occur when there are multiple points that are equally optimal in terms of the objective function value, satisfy the constraints, and exhibit similar optimality properties in the vicinity of an optimal point. Once again, thank you for watching this video. And please consider subscribe to the channel and give a thumbs up to the video. See you soon, hopefully.